Hi, everyone. My name is Rob Messinger, and I'm an assistant professor of chemical engineering at the City College of New York and a core faculty of the CUNY Energy Institute and director of the NASA CCNY Center for Advanced Batteries for Space. So today I'll tell you a little bit about my research group. So as a group, we design, synthesize, and characterize novel materials and devices aimed at solving major societal and technological challenges in energy. Thematically, our group is at the intersection of chemical engineering, physical chemistry, electrochemistry, and material science. So we are a truly interdisciplinary lab, borrowing facets from all of these fields. Our strategy on all of our projects is unifying. We seek to understand and control macroscopic material, transport, and device properties up from the atomic length scale. Particularly, we focus on studying the atomic, molecular, and nanoscales and relating those to macroscopic properties and functions of interest. A bit more concrete, these are three research thrust areas that are currently ongoing in the group. The first is in novel battery materials for electrochemical energy storage. The second is in multi-phase fluids for thermal energy storage. And the last is in multidimensional NMR spectroscopy of energy materials. Within batteries, we have major research efforts in metal ionic liquid batteries, very much aluminum batteries, something I'll talk about in a second. We're also interested in lithium and zinc batteries here. We also work with aqueous zinc alkaline batteries, in particular with collaboration with Professor Sanjoy Banerjee at the City College of New York. With regards to multi-phase fluids, we're interested currently in phase change nanoemulsions, right, where an oil phase can be emulsified, for example, in continuous aqueous phase, and then that oil phase can melt and freeze, thereby storing energy in the latent heat of the phase change. With regards to NMR spectroscopy, we're interested in using this to understand the molecular level compositions, structures, and dynamics of materials. And so we specialize in developing, utilizing advanced and developing methods to characterize molecular level of materials using, for example, dipolar recoupling and multiple quantum methods to understand through space, sub-nanometer scale structures, as well as through bond structures. And so by using a combination of advanced spectroscopic and electrochemical methods coupled with diffraction and imaging techniques, that's how we probe atomic, molecular, and nanoscale structures and relate them to the bulk macroscopic properties of interest. A few words on novel batteries. What are the societal driving forces for current battery research? Well, batteries can help combat global warming and pollution, as well as reduce our dependence on non-renewable fossil fuels. Two ways batteries can meet this challenge is by electrifying transportation. Okay, transportation accounts for about 25% of global CO2 emissions. And life cycle analysis from cradle to grave establishes that EVs and electric transportation in general, whether it's trucks or planes as well as vehicles, passenger cars, reduce emissions. The other is that batteries can enable the integration of renewable energy sources that are inherently intermittent, such as solar and wind, into the grid. And so this is, so batteries are an enabling technology for these renewable energy sources. One of the things I mentioned that we're interested in is rechargeable aluminum metal batteries, right? Because those two applications, electric transportation and grid scale, right, are big batteries, much, much, much bigger in scale than portable electronics. So this is a plot here of the capacity, so the amount of electrons we can store per unit mass in orange and per unit volume in blue of common metal electrodes, and aluminum is here, right? And we get aluminum metal itself can store a large capacity, in part due, or mainly due to the fact that its aluminum cations are 3+, they're trivalent, so one can store 3 electrons per aluminum atom, right? when you're using Al3 plus, it's the working ion. And aluminum, so that describes these high capacities. And aluminum is the most abundant metal in the Earth's crust, and therefore that's correlated with a low cost and mature mining and recycling industries. And it is also inherently safe, right? So it is non-flammable and non-toxic. It's also relatively explored compared to other multivalent metals that use multivalent ions. When you look at the number of scientific publications over time. So there's a lot of opportunities and challenges in this area. One of the things that my group is doing, we're investigating different electrodes and electrolytes for rechargeable aluminum metal batteries. With regards to electrodes, we're looking at different materials such as graphite, organics, polymers, crystalline transition metal chalcogenides, and elemental chalcogenides. All of these, I would say, are emerging electrode materials, and just as the aluminum batteries themselves are an emerging energy storage technology. And so we're interested in not only understanding their electrochemical properties and feasibility, but also, because these are so new, we're interested in studying the ionic charge storage mechanism and electronic charge storage mechanisms, right? So we're trying to figure out, how do these functions up from the atomic length scale using the techniques that I mentioned previously. Okay, so we're studying, so we're doing both technology development and fundamental science in this space. As I mentioned earlier, so I work and direct the NASA CCNY Center for Advanced Batteries for Space, and this is a collaboration between the City College of New York and NASA's Jet Propulsion Laboratory. And we're interested in developing new batteries composed of metal anodes and ionic liquids for robotic spacecraft to enable new planetary science mission concepts. This is in collaboration at City College of New York with Professors Elizabeth Bittinger, Alex Koussis, and Sanjoy Banerjee. We work closely with the Electrochemical Technologies Group, the JPL, and we collaborate with other institutions such as Northeastern University, community colleges within CUNY, and other regional universities. And our goal is to, develop novel batteries that can withstand the extreme conditions, the temperatures and radiation, right, for robotic spacecraft, such as rovers, okay, things that require, for example, high power and low temperature. So this is a Mars helicopter, as well as orbital missions, okay? And so we're looking at different facets of these problems and working closely with JPL. We're very excited about this. Life in the group is dynamic and social. So we're very social. Here's some pictures from our summer barbecue and rock climbing sessions and exploring, Brooklyn and Manhattan. And so our group is social. It's also tight-knit intellectually. And also there's a lot of collaboration that goes on within the group. And so we're a very collaborative social team with a lot of camaraderie. Thank you for listening. My email is rmessenger@ccny.cuny.edu. Feel free to reach out to me if you have any questions. Thank you.